So for topic 11, we'll be looking at measurement, data processing, and analysis. There's 3 topics that we need to know at SL. Topic 11.1, which is uncertainties and errors in measurement and results. 11.2, graphs are a visual representation of trends in data. And 11.3, using analytical and spectroscopic techniques to identify organic and inorganic compounds. The resources that are used for this topic are the Oxford Study Guide, your textbook, which is the Pearson, the standard level, but it's the same information as your high level. And I also use the Cambridge textbook, which is also 2014. So the first topic that we're looking at is uncertainties and errors in measurements and results. We've already started with this at looking at the difference between qualitative and quantitative data. We looked at the difference between precision and accuracy. We looked at calculating the percentage errors, the percentage yields, etc. This is really, really important, and I can't stress enough when we get into our IAs, because most of the marks that you get out of the IA is going to be your ability to basically interpret the results, but also evaluate how well you've designed your experiments and how well you've calculated your results and how well you've interpreted your results given the errors that might arise, and also in terms of the type of equipment that you used. So just briefly, when we're looking at uncertainty, there's 2 types of uncertainties that we can have, things that are random and things that are systematic. Random errors is all related to things that are out of your control. So instrument error, which is caused by the measuring device being used, low precision or accuracy, it is overcome by doing multiple trials and reducing sources of error. However, systematic error is the human error, which can be avoided by better experimental design or techniques. So for example, if I have fluctuation of temperature in the lab, this is going to be random error. But if you've used the wrong thermometer to record your temperature readings, then that's going to be a systematic error. Then in another way of looking at things in terms of the uncertainty, or in a very important part, is to look at the difference between accuracy and precision. Accuracy is basically how close your results are to the true value. So you have a literature value and you're trying to be as close as possible to the literature value. Precision is whether you're able to replicate your results over and over and over again. So for example, you can be highly precise in your measurements and you always get the same answers or as concordant as can be, but they're not very accurate. So you have to be very careful when you're designing your experiment to have both accuracy and precision. So this is a simple diagram to show you the difference between precision and accuracy. So you can have a low accuracy and a high precision, and you can have a high accuracy and low precision, and you can have both low. But what you try to do all the time is to have high accuracy and high precision. The best way to do that is to identify the type of equipment that you're going to be using that are going to be giving you the best results and the best outcomes for your experiment. And I can't stress enough into thinking about the design of your experiment and the type of equipment that you use. And the equipment isn't just about the scale and isn't just about the thermometer, etc. It's also about the type of glassware that you're using. So are you using something that will give you an approximate value? Or are you going to be using something that's going to give you an accurate result? So for example, if you're going to be using a beaker to measure 20 milliliters of volume of a certain liquid, that's not going to be as accurate as using a pipette, for example. So you really need to think about what you are using and how you are going to be using it in the lab, how you're going to repeat your results, and whether that's going to give you the results that you need. Now, how does it all fit in? Here's a worked example asking you to calculate the enthalpy change of a solution, but you need to include the number of significant figures and the percentage uncertainty, etc. So the question says, weigh out approximately 100 grams of water in a polystyrene cup, measure the initial temperature of the water, weigh out accurately approximately 6 grams of potassium bromide, add the potassium bromide to the water, stir rapidly until it has all dissolved, and then record the minimum temperature reached. Use the data below to work out the enthalpy change of a solution to the appropriate number of significant figures. And they've given you the specific heat capacity of water. This is a typical paper 3 question where you've got an experiment and then you need to deal with the answers. So you think about what you've got. You've got the mass of the polystyrene cup, which means that it's empty, and the mass of the polystyrene cup plus water, which gives you the mass of water. So you can see here that I've got the scale, which is to 2 significant figures, and you've got the masses there. So this is of the water. And you will need this because you've got the specific heat capacity of the water, which means that you can calculate Q. Then I have a change in temperature. So here's the initial temperature of the water, and here's the minimum temperature of the water that's been recorded. Then what you also have is the mass of the potassium bromide that you actually used. Again, you can see the scale here. So how do I deal with this question? You take it step by step. So the first thing that you need to do is to calculate the Q. So you go and you figure out the mass of the water. So you can see here that you've got the 105.23 plus or minus 0.01 minus 5 plus or minus 0.01. So you subtract these values from each other. But what you do is that you add these values together. This is because you use the balance twice. Once to measure the empty polystyrene cup, and the second time is to measure it with water. So anytime you have an uncertainty, you add them together if it's the same equipment. So when you subtract 105.23 minus 5, you get 100.23 plus minus 0.02 grams. The next thing that you can do is to calculate the percentage uncertainty of the mass of the water. Now this is really easy because all you need to do is to take out the uncertainty, total uncertainty that you got here, and you divide it by the measurement that you actually have. So here, the total uncertainty was 0.02 because that's the scale. And then you divide that by the mass of the water that you actually used. And because it's a percentage, you multiply by 100 and you get 0.02%. The other thing that you can do from these calculations is to work out the mass of KBR. Because once you measure the mass of the KBR or calculate that, you can find the number of moles of KBR. And by that, you can find the enthalpy change of the solution. So you do exactly the same thing. So you've got the mass with the potassium bromide of the weighing board, and you subtract it from the mass of the empty weighing board. So when you subtract them together, you get 6.11. And because you use the same balance twice, you add these two values together, and again, you get 0.02 grams as plus or minus. So then again, the percentage uncertainty of the mass of KBR is this value divided by this value times 100%. So now I've got the percentage uncertainty of the water and the percentage uncertainty of the KBR. To calculate the change in temperature of water, again, it's the same thing. You subtract the bigger value minus the lower value, okay? Because here it does say initial, and usually to calculate the delta T, we do the the final temperature minus the initial temperature. But here, because we want to get a positive value, we start off with the initial, because what happened is the actual temperature actually dropped. So then you have 21.1 minus 19, which gives you 2.1. And again, because I use the same instrument twice, you can see that here it's plus or minus 0.2 degrees Celsius. So again, you can calculate the percentage uncertainty of the temperature change, which is that value divided by that value, which gives you 19.5%. So I've calculated 3 percentage uncertainties. So the percentage uncertainty of the change in temperature is much larger than the other two uncertainties. So you can see that 9.5 is much bigger than 0.3 and 0.02. What does this mean? It means that most of the uncertainty that we have is because of the change in the temperature and not because of these, because these are very small and they're not going to make much of a difference. So therefore, we can assume that the uncertainty of the final value is going to be due to the largest uncertainty, which is that of the temperature. So then we go ahead and we start calculating. So again, like I said, you can find Q, and we know that Q is equal to mc delta T, where m is the mass of the water because we're given the specific heat capacity of the water. So m is this value here, which is 100.23 times 4.18, which is the specific heat capacity of water, times 2.1, which is the change in the temperature, which gives you 879.6 6.82 joules. Remember that this is in joules, and if you want the delta H, you need to convert that to kilojoules. So, and not only that, because we know that the number of moles of KBr is not going to be exactly 1 mole, because when we go and divide the mass of KBr that we use, which was 6.11, and we divide that by the molar mass of KBr, we get 0.0513 mole, which isn't 1 mole. So to calculate the delta H, we need to divide 879.82 divided by 0.0513 mole. Why is that? Because we know that you've got 879.82 in 0.05 mole. And what we actually want to find out is how much is that in 1 mole. So this is one way of looking at it. So when you do the cross multiplication, you can see that this is going to be divided by 0.0513, sorry. Okay, and then the other way that you can look at it is that delta H is always calculated as Q divided by the number of moles. So either of these would give you the answer that you got here. Okay, and this is in kilojoules per mole. So remember that in order to calculate kilojoules from joules, we need to divide by 1000. So this would have been in joules. So when we divide this by 1000, okay, you would get 17.15 kilojoules per mole. Now, because the question also asked you to calculate the percentage uncertainty of the final answer to the significant figure that we should be using, right? We know that we have to use the 9.5%. So we need to find 9.5% of 17.150. So 9.5% is like saying 9.5 divided by 100 and then multiplying that by 17.15. Okay, so this is how they got that. You divide 9.5 by 100 because that's 9.5%, so it's over 100. And if you multiply that by 17.15, you get 2. So it's to one significant figure. That's the answer that you got. So then the number is going to be 17 plus or minus 2 kilojoules per mole. 11.2 is looking at graphical techniques, and these are the understandings that you need to know. So continuing on with topic 11, the second part is the graphical techniques. This is extremely important when we get into writing our IAs. In fact, the whole of topic 11 is very important for writing IAs because it covers everything that you need to use in order to enhance the quality of your IA. So when we talked about the random and systematic errors and things that basically are going to affect the design of the experiment, these should be included in your IAA, as is the graphical techniques. So a major part of you talking or communicating about the results of your IA is to basically plot it. Okay, and I know that some people graphing might be something that's daunting, but it's actually really easy once you understand how the plot actually works. So I'm hoping that with this session that you'll be able to understand it a bit better. Okay, so I would highly recommend that as we approach the IA writing stage that you keep looking back into this topic and make sure that you include most of the information that I have there, excepting for the spectroscopic analysis, which we'll talk about later. To include it in your actual IA, okay? So back to graphical techniques. These are your understandings and your applications. So there's two ways that we can graph a plotted graph, okay? So we can look at a sketch graph. And a sketch is, just as the name suggests, just a sketch of what's going on. It doesn't have to have a scaled axis, but it does have to have labels. Whereas when you're drawing an actual graph, you must include labels and a scaled axis, okay? So depending on what you're trying to show your reader, you can have a sketch graph, something like the relationship between pressure and volume or the rate of reaction, etc. But in your IA, it's always advisable to move away from sketches and draw an actual labeled graph with a scaled axis. So they will be assessing you on your ability to draw a graph of experimental results and the correct choice of axis and the scale, and to interpret graphs in terms of the relationships of the dependent and independent variables. So let's get back into what a graph contains. So the main purpose of a graph is to show the relationship between your dependent and independent variable, which are part of your research question anyway. So this is here, this is key, where we look at the independent variables, so things that you're basically are changing that are going to have an effect on your experiment. So things like changing the temperature, changing the size, or the particle size, for example, the surface area, the type of metal that you're using, whereas the dependent variable is basically what you're measuring and is affected by the independent variable. We draw the independent variable on the horizontal axis, which means it's on your x-axis, whereas your dependent variable would be on your y-axis. So the best way to show you this is a graph where it shows you the dependent variable, and this is your independent variable. So if I'm increasing the temperature, this will be my temperature, and this is the effect that the temperature has on some sort of outcome that we're trying to measure and find out the information through. So I would highly recommend that you keep revisiting this to remind you of what an independent and dependent variable is and where they're supposed to be basically plotted on your y and x axis. The next points are really, really important as well. So the important thing, number one, is to give your graph a title, and that title should clearly show the relationship between your dependent and independent variable, the effect of temperature on, the effect of the particle size on, etc. You need to label the axis with both quantities and units, which means that if I'm talking about temperature, I need to say what I'm measuring the temperature in. If I'm talking about concentration, you need to talk about moles per decimeters cube, etc. Use the available space as effectively as possible. That means try to get a lot of plots. So that means a lot of coordinate points. The more data you have, the better your graph is going to look like. So make a big graph. Don't just rely on 3 points. Make it bigger. Use sensible linear scales, and there shouldn't be uneven jumps. That means if I'm looking at an axis, I shouldn't go like going by ones and all of a sudden I jump to 5s, to 10s, etc. It should be consistent. So for example, on my x-axis, I can go up by 1. So 1, 2, 3, 4, 5. And on my y-axis, I can go up by 1s, I can go by 2s. They don't necessarily have to be the same on the y and x-axis, but the scaling on each of the axes has to be the same. So for example, an x-axis again can go by 1s, whereas the y-axis can go by 2s. But you have to be consistent and draw them properly. So they have to clearly show the scaling that you've used. A line of best fit should be drawn smoothly and clearly. So the point of a line of best fit is that it doesn't have to go through all of the points, but it has to go through most of the points. Another thing is it doesn't necessarily have to go through the origin, which is 0, 0. That's the coordinate. So in some cases, it's great to have it because it does go through it and most of the points that you have. In some other cases, it does not. So you have to make that decision as to whether you should have the origin point or not. You should also identify any points which do not agree with the general trend. So here, in general, they do lie on the same line. Okay, these ones are a bit above, but in general, they follow the certain trend. So again, with your IA, you are explaining your results. You're trying to make a trend, look at a trend. You're trying to find a pattern. And if there's things that are falling outside of this pattern, you need to be able to explain why. This is an example of extrapolation. That means that most of my data is here, but then I need to extend the line beyond the measurements that I have. So this is basically the best example to give for this one is when we're trying to find the absolute value. So this is why the Kelvin is equal to the degrees Celsius plus 273, because it's an absolute 0. And we do this by the point of extrapolation. Okay, so this is where my data set is, and if I extend the line and it hits the x-axis, then it should hit at that point. This is called extrapolation. Interpolation is the process of assuming that the trend line applies between 2 points. Okay, so you just need to know the definitions of these 2 points, but nothing beyond. You've learned this before, I'm hoping, in math, but to find the gradient of any straight line is to follow this formula, which is y is equal mx plus c. Where x is the independent variable, y is the dependent variable, m here is the gradient, and c is the intercept on the vertical axis. You can easily find the slope as finding the change in the delta y over the change in delta x, so you can make a triangle out of them. Another way that you can find the slope is to draw a tangent. Like for example, if I have this kind of figure here, a curve, okay? If I draw a tangent and where it hits this point here, okay? So at this point here is about 0.1109, okay? So that would be my slope, and then I can find that this is my the slope of my curve, which is basically m. Systematic errors and random errors can often be recognized from a graph, and the best way I can show you this is to look at this point here. This is the key here. You can see that the random errors and the perfect plots are almost on top of each other because the random errors cancel each other out, anything due to fluctuation in temperature, etc., because we're repeating the experiment multiple times. But you can see here with a systematic error, if I have a poor design of an experiment, it's going to be beyond that of the perfect or the random errors. Okay, so this is why your choice of experiment, the type of techniques that you use or the apparatus that you use is extremely important in getting the most reliable data. Okay, so this is one way of showing you this information here. Here is a graph showing an outlier which does not fit the line. So for example, if you get an experimental results and most of your points pass through this, but you have one outlier there, you can explain to say that maybe this happened and this is the cause of it. Most of the points correlate, they are concordant with each other, etc. But this outlier could have been due to something, I don't know, depending on the experimental design that you have. So a main point of you getting more marks on your IA is your ability to explain why this outlier actually happened. So choosing what to plot to produce a straight line, you have to think about the variables that you have, okay? So for example, if I'm trying to plot volume and pressure, they are inversely proportional to each other. They're not going to give you a straight line. But if I do pressure versus the 1 over volume, then I would get a straight line. So you just have to think about whether your variables are directly or inversely proportional with each other. You can also use sketch graphs. Remember that when you were talking about graphs, you can talk about the qualitative analysis and you can talk about the quantitative analysis. Quantitative is anything to deal with the actual data that you have, the measurements that you have, whereas the qualitative data is basically looking at the agreement or the relationship between the dependent and independent variables, whether they have good correlation, not just the quality of the data that you have. You can also use spreadsheets to plot the graph, okay? So using Excel programs, etc. So this is basically it when it comes to doing graphs. So here's other graphs that you have. If you look at here, you can see that most of the plots are concordant with each other, okay? So I don't think that you should really be worried about the graphing techniques. And again, please come back to this topic because it will really help you in understanding the graphical techniques a bit better. The third topic of topic 11, or the subtopic, is spectroscopic identification of organic compounds. So here we're going to be looking at the different techniques that we use in the lab to prove we have what we have. So for example, if I have a hexane molecule, it's very hard in the lab once I make hexane or I use hexane to say that, yep, this is what I have. In order to prove that I have a hexane, I need to use analytical techniques. And the four types that we're going to be using are the IHD, which is the index of hydrogen deficiency. We're going to be using spectroscopic techniques such as mass spectrometry, proton nuclear magnetic resonance, and infrared spectroscopy. So I think the only one that you know at this stage is the mass spec from topic 2, but the others are going to be really easy to understand and use as well. So before we get into all of that, the important thing is to go back to the electromagnetic spectrum. Again, this was covered in topic 2, and to look at the different types of parts of the electromagnetic spectrum. What we have here, which would be the high frequency, sorry, this would be the high frequency, the short wavelengths, and here you would have the low frequency, and the long wavelength. So the lowest ones are going to be my radio waves, and the strongest ones are going to be my X-ray and the gamma rays. So when we're talking about these kind of spectroscopic techniques, we're looking at what's actually happening to the molecule or to the atoms when we are hitting them with a certain amount of energy. So when we look at IR, for example, we're looking at molecular vibration. I need to remind you here that atoms are always moving because the molecules, the electrons are always moving. In the nucleus, the protons are also moving, okay? So the molecule as a whole is always moving, even if I have it at an absolute zero. So when I hit it with energy, it's going to absorb at a specific wavelength. And when it absorbs in that region, this is how we get the spectroscopic techniques, whether they are infrared or we have the radio waves where we're looking at the proton NMR. So here is basically where we have an MRI. I think you know the MRI much more than the NMR at this stage, but they work at the same thing, which is basically looking at radio waves, which are much weaker than looking at infrared. Here's another visual summary of what spectroscopic analysis we're going to be looking at. So this is the mass spectroscopy, which is basically looking at identification of the relative atomic and molecular masses. When we look at the nuclear magnetic resonance, which is the proton NMR, we're looking at the structural formula because it's really going to help you dissect the molecule and tell you how much of the hydrogen atoms that you have in that molecule. And I talk about the hydrogen atoms because it's called the proton NMR. You can have a carbon NMR and other types of atoms as well. But for our purposes, we're just going to be looking at the proton NMR. We're going to be looking at the index of hydrogen deficiency, which is basically abbreviated by IHD. And that basically tells me whether I have single bonds, double bonds, or even cyclic compounds. And the last one that we're going to be looking at is the infrared, and it's abbreviated by IR. And that's basically the absorbance, like I said, of the vibration of the molecules at the specific wavelength after they've been hit by a specific amount of energy. So the nice thing about all of these spectra is that, number one, you don't need to memorize any of the values because all of the values that you need are going to be in your data booklet. And each fragment, each bond, each measurement is specific to a certain functional group that I have. So for example, you'll find out that from the IR, for example, or even from the NMR, that if I have a methyl group, it's going to absorb at a certain region. And if I have a carbonyl group, it's going to absorb at a different region as well. So let's start with the index of hydrogen deficiency, otherwise known as IHD. So basically, this technique is used to identify whether the molecule has single bonds, double bonds, or even a cyclic compound such as a cyclohexane. So there is a specific formula that we use, which is IHD is equal to x plus 2 minus y over 2. So how did we come to this kind of formula? First of all, we need to understand why we do this. So there's a difference between something that's called a saturated molecule and something that's called an unsaturated molecule. Saturated molecule means that each carbon has the maximum number of hydrogen atoms around it. I cannot add any more. So if I look at the hexane here, I can see that each carbon atom has the maximum number of hydrogens around it, and that would allow it to combine with another carbon. So this carbon here has 3 hydrogens, and this carbon is connected to this carbon, which sees 2 hydrogens and 2 carbons on either side. If we were comparing this one to a hexene, I can see that position 2 and 3, I don't have the maximum number of hydrogen atoms around the carbon atoms. This is because 2 of the hydrogen atoms have been replaced by a double bond. So this is why we refer to alkenes and alkynes and cyclohexane, etc., as unsaturated, whereas the ones that are alkanes, they're known as saturated. So it goes to say then that if I was to work out the index of hydrogen deficiency, I need to start with the alkane formula. So the general alkane formula tells me that I have CnH2n plus 2. So if I have any hydrocarbon, I can say that it can be given by the formula of CxHy, where I don't know if I have an alkane, alkene, or an alkyne. So then I put in the formula to say that I have 2x plus 2 to signify that this is my alkane, and to subtract from that the number of hydrogens that I actually have in the molecule, and then divide that by 2. So if I have hexane, which is C6H14, I will see that I have 12 carbons, because it's 6 times 2, which is 12, plus 2, which is the alkane formula, minus 14, which is the number of hydrogen atoms that I have, divided by 2, which gives me 0. This is an expected result because I don't have any double bonds. So the IHD tells me how many double bonds at least I have, or whether I have or I might have a cyclo molecule. So compare that with a hexene. A hexene has the formula of C6H12. So in this case, I have 12 plus 2 again, but this time I'm subtracting 12. And when I divide that by 2, I get 1. This tells me that the compound can contain one double bond, okay? And it can be an isomer of a hexene, or it could be a cyclic compound. So with the IHD, it doesn't actually tell me the structure of the actual molecule, but it does give me an indication that I may have a double bond in there, or I might have a cyclo molecule, depending on how many number of carbon atoms that I have. So in general, this works very well for hydrocarbons because all I care about is just the carbon and hydrogen. But then there are specific rules when I have other atoms, such as oxygen and sulfur, halogens, and nitrogen. In the case of oxygen and sulfur, it's really easy because it does not affect the IHD. You just continue calculating the normal way. But if I do have halogens like fluorine and chlorine and bromine and iodine, they're actually treated like a hydrogen atom. So then I would add 1 to the hydrogen. So here where you added 14, if I had a chlorine, for example, it would be 15, etc. For the nitrogen, it's a bit more complicated than the hydrogen because then I would add 1 more to the carbon and 1 more to the hydrogen. So if I have a molecule like CH3N, I would add 1 extra carbon, so then it's C2, and I would add 1 extra hydrogen, so this is CH5N, then it will be H6. So again, to recap, in order to calculate the IHD, I need to use the general formula for an alkane and subtract from that the number of hydrogen atoms that I have and divide by 2. If I have an oxygen and a sulfur, then I don't need to do anything. But if I have halogens, I add an extra hydrogen for the number of halogen atoms that I have. And for nitrogen, I add 1 extra carbon and 1 extra hydrogen. So the next thing I want to look at is infrared spectroscopy, otherwise known as IR spectroscopy. IR spectroscopy is a specific type of analytical technique that we do or use in the lab, which is very important in helping to identify the functional groups or the bands or the bonds, the type of bonds that I have in a molecule, because it kind of works like a fingerprint region. Each bond will absorb at a specific energy and a specific frequency. So this is going back to the fact that when we look at any molecule, it's always in constant vibration. Even if it's an absolute temperature, you still have atoms that are vibrating. So if you hit it with a specific type of energy, the molecule will absorb this energy and it will vibrate at a specific frequency, okay, or a specific wavelength. And we can quantify that using IR spectroscopy. So the best way to help you understand this is to actually show you what an IR spectrum looks like. So this is an IR spectrum. So let me just delete this so that you can see what we're talking about. So this is the IR spectrum of propanol. Now, how do I know that this is propanol? Because I have a carbonyl group here in the middle. And then I have 2 methyl groups on either side. So prop means I have 3 carbons in a row. Anon means that I have a ketone there. And a ketone simply means that I have a carbonyl group with 2 R groups on either side. Now, if I look at this IR spectrum, I can see that it's measured with the x-axis being the wave number and the y-axis being the transmittance. The transmittance is important because it actually tells me how strong a peak or a band is, and that's indicative of the actual bond that I have. So if you look at the labels that I have here, you can see at this point here, I have a very strong peak at about 1700 that is indicative of a carbonyl group. And then I also have some strong peaks here that are indicative of a CH bond. I also have some strong peaks here which are indicative of the fingerprint region. And these also mean that I have a CH bond there as well. So how do I know what is what? So in order to know that, and this you don't need to memorize, you need to refer back to your data booklet. Your data booklet has all the bonds that you need and what functional group belong to this kind of bond and where they would actually belong or they would absorb at in the IR. So for example, if I have a carbon with a chlorine, which is also known as a chloroalkane, it will absorb between 600 to 800. If I have a carbon to oxygen single bond, it will be between 1000 to 1300. However, if I have a carbonyl group like you saw before, which is indicative of the presence of an aldehyde, a ketone, a carboxylic acid, or an ester, this would absorb with a very sharp peak at between 1700 to 1750. So if I looked at this peak again, I can see that this is indicative of a CO double bond and not a CO single bond. Similarly, if I have an OH group, there are two options that I can have. Either I can have an OH that is indicative of a carboxylic acid or an OH that is indicative of an alcohol. So depending on where you see the OH group, you can classify it as being a carboxylic acid or an alcohol. So to help you see this, this is another example of an IR that belongs to this butanoic acid. From the name butanoic acid, I know that I have a carboxylic acid there. And I can prove this with this kind of spectrum. So here you can see that now I see a very broad but also strong peak around this region that tells me that it's an OH group that belongs to the carboxylic acid. And I also have the carbonyl group there. Now remember, with the alcohol, I wouldn't see this peak there, because if I have a carbonyl group with an OH, that is automatically a carboxylic acid. However, if I have an OH group there that belongs to an alcohol, I would not see this peak here. What I also see is a CO bond, okay, just a single bond, and that is in this region here. So you can see that they are very different to each other. And if I go back to the spectrum before that, you can see that these are very different, and also they're very specific to the type of functional group that you might have. Here is an example of an alcohol. So again, you can see that I have a much higher peak here for the OH. It's still a very strong and broad peak, okay? But what I'm missing here is the peak at 1700. So you can see here, I don't have a carboxylic acid, but I do have an OH group and I do have a CH group. So that clearly tells me that here I have an alcohol. Plus here, I don't have the carbonyl group like I said, but I do have the CO single bond. See that these are very strong. So again, this is a very nice technique because it actually shows you what kind of functional groups that you have and actually see where they belong in the spectrum. So this is another type of qualitative analysis. It doesn't tell you how much of the molecule you have, but it does give you information about the structural formula of this molecule. So let's look at a practice problem here. So I have this spectrum here, and I'm asked to decide which of these four options would be for this kind of spectrum. So I have option A, B, C, and D. So if you look at these options here, you can clearly come to a conclusion as to which ones you can eliminate straight away and which two you would be looking at more closely. But I'm hoping that by this stage, you'll be able to basically decide quickly which molecule it is. So let's see which ones that we can eliminate. So here I can clearly see that I have a very strong peak at around 1700. Because I have this very strong peak, it tells me that I have a carbonyl group. So I can write a note to myself that this must be a carbonyl group there. Because I have a carbonyl group, then I'll look for the molecules that actually have a carbonyl group. This shows me that C and D have a carbonyl group, so that automatically eliminates A and B. What I also see is a very strong peak at about 3000. It's not a very strong peak, not a very broad peak, okay? So that eliminates the OH group, which means the only thing that I can have is option D, which is the ester. If I wanted to prove what I have, this is going to be my CH groups. As I said, this is going to be my CO groups. And you can see that here I have strong peaks here, which are indicative of the CO single bond to the oxygen. So if we look at the answers here, we can see that we can eliminate A, B, and C, okay? And D would be the only logical option because molecule D contains CH bonds and CO bonds and should give rise to a band in the region of 1000 to 1300 because it contains the CO single bond. So as you can see, the IR spectrum is very easy you need to use your data booklet in order to identify the peaks. So if you don't see a peak there, that means it's missing. That means it's not that type of functional group. So my biggest advice there is to look for the strong bands that you have, whether they are sharp bands, like you saw here, or the broad bands like you saw in the alcohols, because they are very indicative of the type of molecule that you have. And like I said, the IR is like a fingerprint. So each bond is specific in a specific region. And so I hope this helps.